So this is our last video of chapter 2. We're going to talk about three-dimensional motion. So this is just a logical extension of some of the other stuff we've been talking about. So we just want to do this from the coordinate and component system perspective to look at 3D vectors and how it impacts some of what we've been working on. So as an example, we look at this sky surfer. So it's this guy attached to this board and he's falling upside down and falling downward and rotating. So he's got some angular velocity theta s, angular acceleration theta s double dot. There's a distance from the axis of rotation to point A on this board, RA, and this guy's falling with a velocity vs. And what we'd like to do is describe the position, velocity, and acceleration of point A as a function of time using some of what we've been doing. So we'll look at this in polar coordinates. So this is like a 3D version in polar coordinates. So it's cylindrical coordinates and there's an r theta and now there's a z component. So r and theta are in the xy plane here, and then z is the z-axis in either the Cartesian or the cylindrical plane. So we have three orthogonal coordinates, r, theta, and z. And so there's three unit vectors, ur hat, u theta hat, uz hat, and uz is ur cross u theta, or ur hat cross u theta hat. And the position vector of this point labeled P here is r, that's this distance here in the xy plane, times the unit vector in the r direction, plus z times the unit vector in the z direction. All right, so this term is this vector here, and this term would be this vector here, and the sum of those two is the little r vector, which is the position vector of point P. Okay, so to get the velocity, we just differentiate that, and this follows with stuff we did before. So you end up with some cross products and you do some simplification and you get an extra term in here from the time derivative of r, right? So if we look back here, to take the time derivative of this, it's r dot times u hat r plus r times ur hat dot, right? Plus the time derivative of this, uz hat is not moving, so it's constant, so it's just z dot uz hat. So what you end up with is three terms. There's the r dot ur hat. There's the r theta dot u theta hat, which comes from ur hat dot, and then the z dot uz hat. Okay, and then this one could just be written as vr ur hat plus v theta u theta hat plus vz uz hat, and the individual components of the velocity are given here. So if you know all these values, r dot, z dot, theta dot, then this gives you the components of the velocity, and you can take the square root of the sum of the squares to get the magnitude. To get acceleration, you just differentiate once more. Again, this is just like what we did before when we talked about polar coordinates. It just got this extra term on it. So when you differentiate that velocity vector, you get a radial component acceleration times the radial unit vector, and a tangential times a tangential unit vector, and then an acceleration in the z direction times the unit vector in the z direction. And the components are given down here. Z double dot is obvious. There's an r theta double dot plus 2 r dot theta dot for the theta direction, and then r double dot minus r theta dot squared for the radial direction. So this is very similar to what we saw in polar coordinates with this extra z component thrown in. You can also do this in spherical coordinates. So in spherical coordinates, there's two angles, phi and theta, and r. So the way it works is r is the position vector from the origin to point P. R without the arrow is the magnitude of that vector. Okay. There's an angle phi, which is measured from the z-axis, an angle theta measured in the xy plane from the x-axis, and then there's unit vectors in those directions. So ur is radial, u theta hat is is in the positive theta direction essentially, and then u phi hat is perpendicular to those two. Again, positive in the positive phi direction or increasing phi direction. Okay, so that's the standard spherical coordinates, and the position vector in this case is just our arrow, our vector is just the magnitude of r times the unit vector in the r direction. So v is just the time derivative of that, and you get a time derivative on the magnitude and a time derivative on the unit vector. It is changing direction. Doesn't change the magnitude, but it does change direction. So it has a time derivative which comes from an angular velocity crossed with that unit vector itself, just like we saw before. Okay, and so omega is the sum of the rotation rates about u theta hat due to change in phi, and a rotation about z-axis due to a change in theta. Okay, so in other words, there's a component of the angular velocity of point P in the theta direction, which is this way, due to phi hat, due to the time rate of change of this angle, and then in the z direction this way, due to theta hat, right, due to rotations about the z-axis. And if you simplify it a little further, then you get, for the angular velocity, a component in the radial direction, which is a rotation about the radial axis, a component in the phi direction, which is a rotation about the phi axis, and then a component in the theta hat direction, right, which is a rotation in the plane perpendicular to that direction. So the velocity can be written like this: a radial component times a radial unit vector, v phi in u in the radial in the unit phi direction, and v theta in the unit theta direction. Okay, and the radial component is just r dot. The phi component is r phi dot. The theta component is r theta dot sine of theta, or excuse me, sine of phi. Okay, if you differentiate once again, you get a radial component, a phi component, and a theta component for the acceleration. And those are given here. They're a little messy, but if you have a functional relationship for r as a function of time, and phi as a function of time, and theta as a function of time, you can work all this out for any angle and find the accelerations at any point as a function of time. Okay, now we can do these in Cartesian coordinates too. We can just take a xyz plane. We can write the position vector as an x component, a y component, and a z component with the usual unit vectors. We can differentiate those. What's nice here is the unit vectors are not moving. They're not changing in magnitude, so their time derivatives are 0. So the velocity is just x dot in the I direction, y dot in the y direction, z dot in the z direction. And the accelerations are just the x acceleration in the x direction, the y acceleration in the y direction, and the z direction, z double dot in the z direction. So this is conceptually much simpler, but for certain problems, these relationships get ugly and are much simpler in either cylindrical or spherical coordinates. So sometimes there is a benefit to using those other coordinate systems, even though this is conceptually much simpler and the differentiation is easier in at this level. So let's look at some examples. The first thing is what's called a precipitator, which is used to pull emissions, particulate emissions, out of the exhaust of a coal plant. So the idea is you have a charged plate, and these particles are charged, and so there's an electrostatic force on them, and we want to know the path of the particle. So particle P is at the origin of this xyz coordinate system at t equals 0. It's launched with some velocity measured by this velocity vector Vp. Okay, and the direction is an angle theta 2 from the x-axis, and then an angle theta, or theta 1 from the x-axis, and theta 2 from the xy plane. Okay, so theta 1 is 30 degrees, so it's 30 degrees out here, and then 55 degrees from the xy plane. And the magnitude is 5 feet per second. All right. This plate is 1.5 feet from the x-axis, and it's in the xz plane or parallel to the xz plane. And so the force from this charged collecting plate on this charged particle gives an acceleration of 250 feet per second squared in the y direction. Okay. There's also gravity on this particle. So there's gravity downward at 32 feet per second, and then there's an acceleration much larger, 250 feet per second squared in the y direction. We want to know, the motion of the particle, all the mechanics of the motion. All right, so we're just going to write F equals ma and break it up into components and then um, solve those equations. Okay, so if we look at this in in terms of components, we can break up this velocity vector for the initial velocity in an x component, a y component, and a z component. The x component is here, VP cosine theta 2 cosine theta 1, right? Because we take this and we take cosine theta 2, that gets us this vector. And that times cosine theta 1 gets us this vector. And VP cosine theta 2 times sine of theta 1 gives us this vector, which is the y component. So the x and y components are given here. The z component is just VP sine of theta 2. All right, so the z component, as I said, is VP sine theta 2. I mentioned these other two. They're on this picture. So the acceleration in this case is can be just broken up as the acceleration in the y direction times the unit vector in the y direction minus g times the unit vector in the z direction. All right, so it's minus because the gravity is acting down. And then this is the acceleration due to that plate, which is 250 feet per second squared. Okay, so we want to say that we want to find when the particle hits the plate. So let's call Tc the time at which it hits the plate. Then it hits the plate when y equals d. And if we write the y position for this constant acceleration case, it's the velocity of the particle in the y direction initially times Tc plus 1/2 the acceleration times Tc squared. Okay, and we know all these. We know d and we know vpy. It's that initial velocity in the y direction, and we know the acceleration in the y direction is 250. So we crunch through the numbers and we get a quadratic equation, for Tc, and we solve that quadratic and we get two solutions. So the first one gives us Tc is negative. Well, we know that's not what the answer is we're looking for. So we find the one positive solution, which turns out to be 0.104 seconds. So it takes a tenth of a second for the particle to hit that plate. And then if you want to know the x and z coordinates when it hits the plate, then you just take that Tc, plug it into the motion result for the x direction. It's got no accelerations there, so it's just the initial velocity in the x direction times the time. It ends up being about 0.258 feet. And then for z, it's constant acceleration in the negative z direction, so it's the initial velocity in the z direction times the time minus 1/2 g, which is the acceleration in the z direction, times Tc squared, which is also about 1/4 of a foot. So if you were to look at the trajectory, the particle's ejected this way, and then because the acceleration is so high, by the time it hits that plate, it's heading almost straight downstream in the y direction, and the gravity gets overwhelmed by the acceleration in the y direction. All right, the last example is a crane. It's a so-called top slewing crane. So there's this tower, vertical tower. It can rotate, right? So it's got this boom hanging out at a distance, some distance out from the center of the rotation axis. There's something hanging, okay? So then this thing can rotate about this tower. So there's a rotation velocity of 0.15 radians per second. And then this is being hauled up by the crane at 1.5 meters per second, and we want to understand the velocity and acceleration of this thing we're hauling around um, as a result of these two motions, the rotation of the crane and the raising of that object. All right, so we'll use polar coordinates for this, mainly because this rotation about the axis makes that simple. Okay, so VC, as we saw before, is just r dot UR hat plus R theta dot U theta hat plus Z dot U Z hat. Okay, it's just the thing we derived before, and the acceleration is given here. Again, it's things we derived before. The radius from here to here is 45 meters. That distance is not changing. Okay, you might have a situation where point A is moving, but in this case it's not. So R dot is 0, R double dot is 0. Z dot is the vertical velocity of point C. It's 1.5 meters per second given, and then theta dot is 0.15 radians per second. So we just plug all this into here. We find that the velocity of point C is 6.75 meters per second in the theta direction, which in this case would be into the board, and 1.5 meters per second in the z direction, which is given to us, and it's vertical. And then the acceleration, part C, is just in the radial direction, and it's minus 1.01 meters per second squared. Remember, when something's moving around in a circle, there's a radial acceleration as a function, as a result of that. It's this term right here, r theta dot squared times ur hat. And it's negative because it's inward towards the center of the rotation. Okay? So that's about it for 3D. There is one conceptual problem to discuss. There's this picture of a spherical coordinate system, and the question is, are there any errors in this picture? Well, you can pause this and think about it if you want, but the solution is down here. The main thing is that this polar angle phi is supposed to be measured from the z-axis, and if you measure it from the wrong axis, it throws everything off. So because of that, the formulas we derived would not be correct. All right, that's it for now.